All right, get ready, because today we're going deep into a world where even tiny glitches can cause massive problems.
Oh, yeah.
We're talking performance regressions,
Mm-hmm.
those sneaky little code changes that can just slowly drain resources and end up costing companies tons of money.
Yeah.
And you might be thinking, well,
Yeah.
how bad can a small glitch really be?
Right.
But imagine if you have a performance dip so small that you don't even really notice it,
Right.
except it's happening on like thousands of servers.
Yeah. That's the challenge that Meta faces every single day.
Oh, wow.
Even just a tiny 0.005% increase in CPU usage
Wow.
can become a huge waste when you're operating at their scale.
Yeah.
It all adds up.
That's wild.
Yeah.
And that's exactly why Meta created this tool called FBDetect.
Right.
It's their secret weapon for hunting down these performance problems.
Yeah.
We've got this academic paper here that really pulls back the curtain on FBDetect, how it works, how it's been tested in Meta's production environment, and most importantly, what we can learn from it,
Yeah.
even if we're not running something at Meta's scale.
I think it's really fascinating how much we can actually learn from Meta's approach.
Oh, yeah, for sure.
They've come up against and solved some really unique challenges in order to catch these tiny regressions that most monitoring systems would completely miss.
And that's because traditional testing just doesn't cut it when we're dealing with these kinds of performance issues.
Yeah.
Like, you can try to simulate the production environment all you want,
Right.
but it's never going to be quite the same as the real deal.
Yeah. And by the time you catch a tiny regression in pre-production,
Right.
it might be too late.
Exactly.
Yeah.
So FBDetect takes a different approach.
It does.
So instead of just relying solely on pre-production testing,
Right.
it's constantly monitoring performance in production.
It is.
So it's analyzing these massive streams of data from various service metrics.
That's right. Yeah.
So it's like this watchful guardian just constantly looking out for any sign of trouble.
But here's where it gets really interesting.
Okay.
So FBDetect doesn't just look at the overall performance of a service.
Right.
It actually zooms in on the individual functions within that service.
Okay.
And it analyzes performance at the subroutine level.
That's a really key innovation.
Wow.
It's like if you're using a microscope to find like a tiny crack in a smooth surface.
Right.
By looking at performance at this granular level,
Yeah.
FBDetect can actually see much smaller regressions than traditional systems can.
Okay, so I'm trying to wrap my head around why that is.
Sure.
Is it just because they're looking at smaller chunks of code?
It's more nuanced than that. When you look at the overall performance of a service, there's just so much variability. Like the traffic fluctuates, different tasks are running in the background.
Sure.
All sorts of things can cause these temporary spikes or dips in performance.
So it's kind of like trying to listen for a whisper in a really noisy room.
Exactly.
But when you just focus on one specific subroutine, you filter out so much of that noise.
Okay.
And the performance of a single function
Right.
is just much more stable.
Right.
Which makes it way easier to see even these really tiny deviations from the norm.
Okay, that makes a lot of sense.
Yeah.
So they got this really granular view of performance. But how do they actually measure performance at that subroutine level?
So they use this technique called stack trace sampling.
Okay.
It's essentially a way to figure out what code is actually running at a particular point in time.
Okay.
Now, for languages like C++, it's actually pretty straightforward.
Okay.
But for interpreted languages like Python,
Right.
it gets a bit tricky.
Why is Python so different?
Well, when you sample a stack trace in Python, what you're often getting is the interpreter's stack trace, not the Python code that you're interested in. Like trying to figure out what's going on inside a building. But you're only allowed to look at the street outside. You might see people going in and out, but you really don't know what they're doing once they're inside.
Okay, so Meta had to develop a specialized tool just for Python.
They did.
Okay.
They created PyPerf.
Okay.
It's a profiler that uses a technology called eBPF.
eBPF.
Okay.
I'm going to need you to break that down for me.
Sure.
It sounds like something out of a sci-fi movie.
It's a really powerful tool that lets you safely hook into the Linux kernel.
Okay.
And essentially, it gives you this window into how the operating system works.
Okay.
In this case, it's used to track how Python code actually executes
Okay.
at a very low level. And it gives you that stack trace that FBDetect needs.
So it's like having X-ray vision for your Python code.
Exactly.
Well, that's amazing.
And as far as I know, PyPerf is actually the first profiler that can give you a complete stack trace that covers both the Python code and any underlying C or C++ libraries it might be calling.
Wow, that's impressive. So now they've got all of this incredibly detailed data.
Right.
About what's happening inside their Python code.
Yeah.
But the next challenge is what to do with all that information.
Mm-hmm.
Right? Not every change in performance is a real regression.
That's right.
Right? That needs to be fixed.
Exactly.
Right? That's where the problem of false positives comes in.
Right.
So false positives, like when the smoke detector goes off, but you've only burned toast.
Yeah, exactly. So in this context, a false positive is basically when FBDetect flags a performance change. That's not actually a problem.
Okay.
It might look like a regression.
Right.
But it's actually caused by something completely normal.
So like what?
Okay, so let's say a developer refactors some code and moves a piece of functionality from one subroutine to another.
So the work is still being done, it's just in a different place.
Exactly.
Okay.
The overall cost of that operation might be the same, but FBDetect might see a dip in performance in that original subroutine and then flag it as a regression.
Okay.
So we call those cost shifts.
Okay, I can see how that would happen.
Yeah.
So they need a way to tell the difference between a real regression and just like a rearrangement of the furniture.
Exactly.
Yeah.
And then you've got those transient issues that we talked about earlier.
Yeah.
So let's say a server briefly has a little hiccup
Okay.
because of a network glitch or something, or a background task just momentarily hogs a bunch of resources.
Yeah.
That can easily create a temporary drop in performance.
Right.
And we don't want FBDetect to trigger an alert every time a server basically sneezes.
Right.
Because that would just overwhelm the developers with false alarms.
So they need to find a way to filter out all of those temporary blips.
Exactly.
So FBDetect needs to be smart enough to ignore those.
Right.
What are some of the strategies that they use to deal with all these false positives?
Well, they have a whole bunch of techniques. Okay.
But one of the most interesting ones is how they deal with cost shifts.
Okay.
Remember we talked about how just moving code between subroutines can make it look like there's a regression?
Yeah.
Well, FBDetect has a really clever way of dealing with this.
Okay. I'm all ears.
So instead of just looking at that individual subroutine, FBDetect also analyzes these things called higher-level cost domains.
Cost domains?
Yeah. It's kind of like think of it this way, like if a company decides to reorganize its departments and they start moving employees around.
So people are shifting roles, but the overall work of the company stays the same.
Exactly.
Okay.
And in a similar way, FBDetect looks at whether the total cost within a certain domain, like a whole class or a set of related functions, has changed.
All right.
If the cost hasn't changed significantly, even if one subroutine shows a dip, it flags it as a potential cost shift.
So it's basically checking to see if the work is still getting done, even if it's being done by a different team, so to speak.
Exactly.
Okay, that's pretty clever.
Yeah. But what about those temporary glitches that we were talking about earlier?
Right.
How does FBDetect know if a performance dip is just a blip?
They've got a few strategies for that.
Okay.
One technique is they combine what's called change point detection, which helps identify anomalies in the data with trend analysis.
So they're looking for than just like a blip on the radar.
Right.
They're looking for sustained change over time.
That's right.
Okay.
They also have this thing called the went-away detector.
The went-away detector.
Which analyzes the performance data in this interesting way.
Okay.
It's almost like turning it into a secret code. And if this weird pattern appears and then vanishes quickly, FBDetect is like, oh, okay.
Right.
That was just a temporary glitch. We don't need to worry about that.
So they're teaching it the normal language of the system?
Yeah, exactly.
And then flagging anything that looks out of place.
Right.
Interesting.
So it's all about finding that balance between being sensitive to the real regressions, but not getting bogged down by all the temporary noise.
Right, because if you have too many false positives, then people are just going to start ignoring all the alerts.
Exactly.
Okay, so they have all these checks and balances in place that help FBDetect filter out all of the noise. But what happens when you have a single code change that causes like multiple anomalies?
That's a great point.
Wouldn't that lead to just like a ton of redundant alerts?
Yeah, you don't want to be bombarded with alerts for basically the same problem.
Right.
So to deal with that, FBDetect has this two-step deduplication process.
A two-step process.
So the first step uses this fast clustering algorithm called SOMD-DUP.
SOMD-DUP.
Think of it like you have this giant mountain of alerts, and you need to quickly sort through them.
Yeah.
SOMD-DUP basically groups similar alerts together.
Okay.
Kind of like if you were pre-sorting your email inbox.
So it helps just declutter that initial wave of alerts.
Exactly.
Okay. So what's the second step?
So the second step is called pairwise dedup.
Okay.
This step is a bit more thorough. It compares regressions across different metrics and across different time windows to see if they were actually caused by the same underlying change.
So it's like going through that pre-sorted email and making sure that those seemingly different emails are actually about the same thing.
Exactly.
Okay, that makes sense.
Yeah.
So they've analyzed all this data. They've filtered out the false positives. They've deduplicated redundant alerts.
Yeah.
What's the final piece of this puzzle?
The final and arguably most important step is root cause analysis.
Root cause analysis, okay.
And this is where FBDetect puts on its detective hat and tries to figure out exactly which code change or which configuration change is responsible for this performance regression.
So this is where they really try to pinpoint the culprit.
Exactly.
Oh, okay.
They have a few techniques they use for this. For example, they analyze which subroutines are modified by a particular code change. And then they see how their CPU usage is affected by the regression.
So if there's a code change description that says like optimizing function X, and then FBDetect sees a performance dip in function X, it's a pretty good clue that those two are related.
Exactly.
Okay.
And they also use text analysis to actually compare the code change description to the context of the regression.
Okay.
If there's a semantic match, meaning like the words and phrases are similar, that adds more evidence to the connection.
So they're not just looking at the code itself, they're actually using the descriptions that humans wrote to help put the pieces together.
That's right.
Okay, that's pretty clever.
It is.
And they even look for correlations. Between performance metrics and other things happening in the system. Like, for example, if they see a regression that happens right when a certain feature flag is turned on or off, that's a really valuable clue. It's like they're using every piece of information they can to solve this mystery. This all sounds really impressive. But how does FBDetect actually perform in the real world?
That's where it gets really interesting.
So tell me, does it actually live up to all the hype?
The results are pretty amazing.
Okay.
So first of all, we're talking about a system that's monitoring like 800,000 time series.
800,000?
Across hundreds of different services at Meta.
That's mind-boggling. And it's not just for like one specific type of workload, right?
No, it's one of the key things about FBDetect.
Okay.
It's super versatile.
Yeah.
They've deployed it on all sorts of different workloads.
Wow.
Everything from their serverless platforms for PHP and for Python to their huge Grash database, their ad serving systems, even their invoicing system.
So even something like invoicing, which you wouldn't think would be super complicated, needs this level of performance monitoring.
Yeah. It's really interesting. And the paper goes into some detail about how they actually configure FBDetect for these different workloads.
Okay.
Because some systems need to be able to detect really big regressions super quickly, while others need to be able to catch those really tiny ones that are almost invisible.
Right.
It depends.
So how do they evaluate whether it's working?
Well, they've been using it in production for years.
Oh, wow.
So they have tons of real-world data on how it's performing.
Okay.
It's been really rigorously tested.
So what's the verdict?
The results are really compelling.
Okay.
First, they wanted to see how good FBDetect was at reducing those false positives.
Right, those alerts that just send developers on wild goose chase.
Exactly, and they found that it drastically reduces the number of false positives.
Oh, wow.
Sometimes by orders of magnitude.
That's huge, because that frees up the developers to actually focus on fixing the real problems.
Exactly.
Not just chasing down these phantom issues.
Right, it makes the whole system much more trustworthy. If you're constantly getting bombarded with false alerts, you start to tune them out.
Yeah.
And then you might miss a real problem when it comes up.
It's like the boy who cried wolf.
Exactly.
Okay, so they're avoiding those false alarms.
Yeah.
But are they catching the actual regressions?
Right.
What about the false negative rate?
So they analyzed an entire year's worth of performance data for one of their really important services.
Okay.
And they found that FBDetect hadn't missed a single regression that it was supposed to catch.
So it's incredibly accurate.
It is.
That's really impressive.
And they didn't just test it internally.
Okay.
They actually compared FBDetect to another well-known anomaly detection system. It's called EGADS.
EGADS.
Developed by Yahoo.
Right. Okay, so how did it stack up?
FBDetect actually significantly outperformed EGADS, especially when it came to catching those small regressions, while still keeping the false positives low.
Right.
EGADS just really struggled to find that balance.
Wow. Okay, so FBDetect is like in a league of its own.
Yeah.
What about the root cause analysis part?
Right.
How good is it at actually pinpointing the specific change that caused the problem?
Well, it's not perfect.
Sure.
But it's actually really good.
Okay.
So in their evaluation, whenever FBDetect suggested a root cause, the developers said it was correct about 71% of the time.
Oh, that's really high.
It is.
Considering how complicated these systems are.
Yeah, and even when it didn't give a specific root cause, the developers often couldn't find one either.
So it's not always a simple thing to figure out.
Exactly. Sometimes a regression is the result of a bunch of tiny little changes.
Right.
Or it's caused by a complex interaction between different parts of the system.
So it's not really that FBDetect is failing.
Right.
It's just that it's reflecting how complicated these systems really are.
Yeah.
But overall, it sounds like a really impressive tool.
It is.
It's really amazing that it can detect such small regressions.
Yeah.
Remember we talked about that 0.005% increase in CPU usage?
Yeah, that seemed tiny.
Yeah, it seemed almost insignificant.
Right.
Well, it turns out that those tiny regressions actually make up a huge portion of the regressions that they catch.
Exactly.
That's wild.
It really highlights how important it is to have something like FBDetect.
Right.
To catch these things before they can really add up.
It's like the saying, take care of the pennies and the pounds will take care of themselves.
Exactly.
So before we wrap up, I'm curious about that Python profiler that they created.
Right.
PyPerf. So does all of this detailed stack tracing come at a cost?
That's a great question.
Like, is there performance overhead?
So any performance monitoring tool has to be lightweight.
Right.
You don't want it to slow down the system that it's trying to measure.
It's like you don't want the observer to interfere with the experiment.
Exactly.
Okay, so what's the overhead like for PyPerf?
So they tested it using a benchmark that was really heavy on CPU usage.
Okay.
And they found that at the sampling rate that they use for their Python serverless platform, PyPerf had basically no noticeable impact on performance.
So for most applications, it's pretty much invisible.
Yeah.
But what happens if you need to sample more frequently?
So they really pushed it to the limit.
Okay.
They collected a sample every single second.
Wow.
Even then, the performance hit was only about 0.8%.
That's incredibly efficient, especially considering that they're capturing a full end-to-end stack trace.
Yeah, it really shows how clever the design of PyPerf is.
Right.
And the power of eBPF.
Okay, so we've covered a ton of ground here.
We have.
What's the key takeaway for someone who's not running a global scale system like Meta?
I think the big takeaway is that even tiny regressions can really make a difference, especially as your system grows.
Yeah.
And FBDetect shows that it is possible to create these tools to catch these regressions early before they become huge problems.
Yeah, and it's not just about the specific tools.
Right.
It's about the whole mindset of constantly monitoring and analyzing performance.
Exactly, being proactive, anticipating problems, and trying to solve them before they affect users or waste resources.
And that's a really valuable lesson for any system, no matter how big or small.
Yeah, absolutely.
It doesn't matter if you're working on a massive social network, a complicated web application, or even just a side project in your free time.
Yeah.
So FBDetect is really cool, but it made me think about all of the other metrics that might be just as important as CPU.
Yeah, CPU usage is just one piece of the puzzle.
Right.
There's a lot more to think about.
Exactly.
And especially for different types of systems.
Yeah, so what are some of the other metrics that people should be thinking about?
Well, let's think about latency, for example.
Yeah.
A small increase in latency might not be noticeable right away.
Right.
But if it's happening all over your system, it can make things feel really slow for users.
Yeah, and that can be a big problem for businesses that really need things to be fast and responsive.
Exactly.
What else?
Well, what about memory leaks?
Okay.
A small memory leak might not seem like a big deal at first.
Yeah.
But over time, it can keep growing until it crashes your entire application.
It's like a leaky faucet that eventually floods your basement.
Exactly. It's something you definitely don't want to ignore.
No, you don't.
And then you've also got things like error rates.
Right.
Even a slight increase in errors could be a sign that there's a bigger problem that needs to be fixed.
So it sounds like FBDetect is really just one example of how we can tackle these performance issues.
It is.
But the real lesson here is to think about the metrics that matter most for our specific systems.
Exactly. You have to figure out what's important for your context. And then use those principles of monitoring and analysis to find and fix problems before they get out of control.
So the next time I'm working on optimizing some code, I shouldn't just focus on speed.
Right.
I should be thinking about all the different ways I could be wasting resources.
Absolutely. And sometimes the simplest tools are the best ones.
Right.
Don't underestimate how useful it can be to have a simple dashboard that helps you visualize those trends and anomalies.
It's true. Sometimes the fanciest algorithm is useless if you can't even figure out how to use it.
Exactly.
Well, this has been another amazing deep dive.
It has.
We've learned about performance regressions and how Meta deals with them.
Yeah.
And even picked up a few tips we can use in our own projects.
Yeah, definitely.
If you enjoyed this deep dive, be sure to subscribe for more insightful and entertaining journeys into the world of tech research and all things fascinating.
We'll have more great deep dives coming soon.
So stay tuned.